consider linear transformations between coordinate systems or just the natural representations of vector spaces over fields. And in particular, we're going to develop the idea of a matrix. So to do this, let's begin with the following. A linear transformation T from f to the m to f to the n can be described quite explicitly in a way that is very convenient for calculation. This will be the matrix. The image of its basis vector delta j within Fm is a linear combination of basis vectors delta I in Fn, so that delta T of delta j is equal to the sum is a linear combination of each of the delta i's for some scalars aij in F. Therefore, by linearity, we can write the image of a arbitrary vector v is a set from of xj delta j's within f to the m, with the coordinates xj being the vector w is equal to t of v is equal to the sum of xj t delta j is equal to the double sum over j and over I of xj aij delta I. That is, remember that t delta j, each of these terms is itself a sum that can be written in this way, and therefore you can pull out the x to the j term over in a sense, and you have the aij's, and then you have to sum over each of these indices. I'm sorry, that's incorrect. You should put the xj inside the transformation after you turn it into a sum. That is, there is a step where you have an xj between these two sums, and then your inside is aij delta I, and then you move that xj inside by using the properties of sums. With this double sum, you can also write this double sum as a sum over simply the n vectors by reordering these indices, since we're considering finite sums. And therefore, if you change the sum with this one, this xj aij will make a new set of elements yi, and you can use those to sum over to give your coefficients for delta I. And as we'll note that the coordinates yi are given as this sum of 1 to m aij xj. That is, for instance, y1 is equal to the sum from 1 to m of a1j xj, where j is the one running from 1 to m. Therefore, a linear transformation can be completely described by the set of scalars aij within F. That is, when we're doing this transformation to make w out of which is written in terms of xj's, to write them in terms of yi's, we simply need all of these numbers aij's. And noting that a linear transformation is another way is just think about that as rewriting a vector. It is customary and convenient to list these scalars in an array of the form this, where a is equal to a11 all the way up to a1m, and then taken down to anm. That is, you have n rows down and m columns along. And one way of remembering this is that if you have n by m, which is an n by m matrix, that means the linear transformation is taken from fm to fn. And if you were familiar with matrix multiplication, you can see that by multiplying by an m by 1 vector here to produce an n by 1 vector. We'll see that soon if you're not familiar. We call this an n by m matrix over the field F, where it's because it's over the field F, that means each of these aij's are taken from F. An n by m matrix with entries in the field F thus describes the linear transformation T from Fn to Fn, and that convention should be kept firmly in mind. That is, each linear transformation can be described in terms of these, entries. And we'll also see that the entries uniquely describe a transformation. The horizontal lines are called the rows of the matrix, and the vertical lines are called the columns in the standard way. So an n by m matrix can be viewed as n row vectors, so this one, etc. Or you can view it as a collection of m column vectors, this one, and so on. The scalars aij are called the entries of the matrix, so A is equal to the set of aij's, where aij is the entry in row I and column j. Usually use this if you have a formula for generating the aijth element depending on I and j. The linear relations between the coordinates xj of a vector in Fm and the coordinates yi of the image vector in Fn is 1.52, namely in this sense. That is, you can express w vector in terms of the delta i's using yi's, or you can express it as in terms of xj's using t of delta j as each of your terms. That is, because you applied linearity, you can put the xj inside, and you can derive it as t of xj delta j, where that is just v. So v is the xj delta j's, as you can see here, and then w can be written as a sum of yi's delta i's, where delta i's are taken as a basis of f to the n, i.e. there are n of them. This idea about how to think about a matrix is very rigid and therefore should be followed strictly and systematically. With that, we've generated the idea of a matrix. So next time we're going to consider the space of matrices and check out their structures. Thank you.